And now we are live.
Okay, so 2 minutes, probably more, and we will start. Okay, hello everyone. This is Anna Bartkiewicz at Nicolaus Copernicus University in Toruń, Poland. I am very happy to welcome you on behalf of the organizing committee to this second series of seminars sponsored by the European VLBI network focusing on high-resolution radio astronomy. Let me mention a few logistics. You will be muted throughout the presentation, but you are invited to type any questions you may have for our speaker through the Q&A Zoom facility or in the chat at the YouTube channel. Questions will be answered only after the presentation. Please try to write your questions clearly and keep them short. We will aim to get to as many of your questions as we can, and we apologize in advance if your questions is not among those we have time to answer. Now, Denise Gabuzda from University College Cork will introduce today's speaker, Cornelia Lang.
Thank you. And I see there's a few people from UCC there and amongst the participants, and it's good to see you. Today's speaker, Cornelia Lang, is a professor in the Department of Physics and Astronomy at the University of Iowa, where she's been since 2002. Before that, she received her PhD in astronomy at the University of California, Los Angeles, and also spent time as a postdoctoral research fellow at the University of Massachusetts Amherst. Her research interests focus on understanding the astrophysics at the center of our Milky Way galaxy and of other nearby galaxies using radio, infrared, and X-ray observations. Her research group includes both graduate and undergraduate students. Cornelia is part of the leadership of the International Astronomical Union Division H's working group on the Galactic Center, which works to bring together international scientists around studies of the Galactic Center. And today she'll be telling us about high-resolution observations of magnetic fields in the central molecular zone of the Galactic Center. And over to you, Cornelia.
Okay, thanks so much. Can everybody hear me all right? Great. Yes. Good. So I think I'll start my slide deck. I want to start by just thanking the organizers for the invitation, and thanks for all of you who are attending in different time zones. I see lots of friends and collaborators and colleagues on the participant list, and I look forward to the discussion afterwards. All right, so I will start by sharing my screen. Let's see. Oops. Where to get? There we go. All right. Does that look okay?
Yes.
Great. So I'm very pleased today to be talking about a wide variety of size scales and observational techniques. So I'll be talking about high resolution observations of magnetic fields in quite a large region of the Galactic Center, a region that we call the Central Molecular Zone, which is a region that is roughly 200 to 300 parsecs along the galactic plane and extends about 50 to 75 parsecs above and below the galactic plane. And so I'll be talking about magnetic fields throughout this region, traced both in the interstellar environment and also within molecular clouds. So I've actually put quite a long introduction together for the talk today because I know we have a wide variety of participants and students. My graduate student, Dylan Paré, is here in the audience, and I'll be highlighting a lot of his work. So I'm going to talk a little bit for those who don't have a lot of expertise in studying the Galactic Center about how we actually observe the Galactic Center. There are some challenges. And because this is a seminar with EVN, I thought I would also highlight some contributions that the techniques of VLBI have made to our understanding of the Galactic Center. So I'll briefly touch on a little bit about the overall properties of the central molecular zone, but then I'm going to focus on what we know about the magnetic field in this region, again, from very large scales to very small scales. And then toward the end of the talk, I'm going to highlight a particular tracer, a really exciting tracer of the magnetic field in the Galactic Center, perhaps the most stunning, which are the non-thermal filaments. And I'm going to highlight some of the absolutely fantastic results, even coming out this week from the Meerkat telescope in South Africa. And then I'm also going to highlight 3 recent studies from my research group using the Very Large Array and the Australia Telescope Compact Array. So first of all, I always want to make a shout out to my research students and collaborators. This is a picture pre-pandemic where we stood next to each other and didn't wear masks. And you can see Dylan Paré, who's graduating this spring with a PhD in physics from the University of Iowa, is here in the middle, and he's here on the Zoom today. And some of my undergraduates have gone off to graduate school now since this picture was taken. So just to get us all oriented and all on the same page, this is a beautiful rendition, a kind of top-down sketch based on what we know about the size and structure of our Milky Way galaxy. And you can see the sun is located here at the end of the yellow arrow. And the Galactic Center, from our perspective, going around the sun, is a southern object. It's in the direction of the constellation Sagittarius. And from the southern United States, where I do a lot of my observing, the Galactic Center is observable 4 to 5 hours a day during the summer. From Australia, of course, and other places in the southern hemisphere, you can observe the Galactic Center a lot more of the time every day. And so a lot of fantastic observations, like the data from Meerkat, like the data from the Australia Telescope Compact Array, have been made from the southern hemisphere. We know now the distance between the sun and the center of the Milky Way to be about 25,000 light years, or 8 kiloparsecs. And as you can imagine, looking in the direction of the center of the galaxy through about 25,000 light years of gas and dust provides some very significant challenges to observing this region. So we all know that there is significant visual extinction toward the Galactic Center, about 30 visual magnitudes of extinction shown in this optical image toward the Galactic Center, where you can see these very, very strong dust lanes. But we know that we can use other parts of the electromagnetic spectrum to study this area in a lot of detail. And so I showed just one stunning Spitzer Space Telescope image of the Galactic Center taken in the near infrared, mid-infrared, where you can start to see the structures that are associated with the Galactic Center, the region near the center, the arched filaments and radio arc region, Sagittarius B, Sagittarius C. You can start to see them emerge through the very strong extinction. And that helps us really understand the ecosystem in this region. So I thought for those who aren't as familiar with some of the different observing techniques, we'll just take a moment to talk about the various ways in which radio astronomy in particular has contributed deeply to the understanding of the Galactic Center. We're going to be focusing today in my talk on radio continuum, primarily non-thermal emission, although there also will be some mention of thermal emission. So I thought I'd just take you through the different tracers that we use. So one of the ways that we've learned a lot about the interstellar medium is to use radiospectral lines. So there's a wide variety of spectral lines used, more and more opening up with the advent of fantastic submillimeter and millimeter telescopes. And so these trace the atomic and molecular component in the galactic center and give us a lot of sense about this potential for this region to form new stars. We also use radio recombination lines, and these are tracers that tell us about ionized gas that's been heated by massive stars. The bulk of the observations of the Galactic Center have been made in the radio continuum. There you have a combination of both synchrotron, magnetized emission, or free emission. And the beauty of the synchrotron emission is using radio telescopes, you can study the linear polarization, which unlocks a lot of clues to the structure and origin of the magnetic field that is traced in this component. We also have relied heavily in Galactic Center science on near-infrared continuum, and that has just opened up a wealth of information about the actual stars that exist in this region. It's also unlocked the potential for us to discover that there is a supermassive black hole at the very center of the galaxy. Recently, we've been focusing a lot on mid-infrared continuum with the advent of higher resolution telescopes in space. And the mid-infrared tells us about re-radiated starlight as traced by dust and clouds. And what's exciting about the mid-infrared is that the dust grain alignment in this region of the electromagnetic spectrum can reveal clues about the magnetic field within clouds. And then finally, we've also learned a tremendous amount about the Galactic Center through X-ray continuum and line studies. And so you'll see in the panels on this image, you'll see a beautiful montage that we made about 10 years ago now, showing the combination of near infrared in the yellow, very high resolution traced by Hubble Space Telescope, mid infrared, an X-ray, and then down at the bottom, you'll see some free emission surrounding the supermassive black hole in the northern arm structure. And then you'll see an example of the radio synchrotron filaments that we'll be talking about in this talk. I also just want to point out that there has been a huge critical role to understanding our galactic center made by the advent of VLBI techniques over many, many decades. And some of the experts in this and major contributors are on the call today, but I'll just name a few of the key results that have allowed basically the rest of my talk to happen. The size and structure of Sagittarius star in the immediate environment, including observations of variability on various timescales, has been made possible by VLBI observations. We've learned a lot about the polarization and rotation measure of the source associated with the black hole itself. A huge improvement to our understanding of the size and structure of our galaxy has been made by determining the distance to the galactic center using proper motions of masers in this region. And of course, we have the stunning and exciting EHT observations of the galactic center supermassive black hole that are expected. And so on the right, I just show again, this is a VLA, very high resolution image. So it's not a VLBA image, but the VLBI and VLBA images have contributed a lot to our understanding of Sagittarius star, which is that bright point source right there at the center of that beautiful streamers of gas in the central few parsecs of the galactic center. So let's zoom out for a minute, talk a little bit about a few properties, and then we'll turn to really why we're interested in the magnetic field in this very unusual region. So one thing I want to point out is that this image is showing the central molecular zone. So you can see the scale bar here represents about 50 parsecs. So you can see the long axis of this image is about 200 or 300 parsecs, and the height is about 100 parsecs. And you can see some of our very familiar sources labeled here. And a couple of key things that we've learned about the central molecular zone. And again, lots of people involved in this call and throughout Europe and have contributed recently to our understanding of this region in even more detail. So this is an area that is a reservoir of dense molecular gas. This is traced in a number of high density tracers such as ammonia. So you can see the red in this image is from an ammonia survey. You can see that the total mass is about 10 to the 7th solar masses, with densities in a lot of the molecular component of about 10 to the 4th per centimeter cubed. We also know that the gas is distributed in this very unusual sort of thin elliptical sheet of gas. And there's been a lot of work done on understanding the unusual not permitted orbits of molecular clouds and how that might contribute overall to an understanding of how star formation proceeds in this unusual environment. There have been a lot of great ideas about streamers of gas coming in close to the potential around Sagittarius star and that triggering star formation. That's sort of a general idea that may be taking place. But we do know that the conditions in the central molecular zone are similar to distant starbursts. So there's some nice potential analogies that studying our galactic center might open up for us throughout the universe. If we zoom in now to this smaller region, this is a region that's about 100 parsecs by 75 parsecs or so. This is the region that includes Sagittarius and the key energetic activity associated with the radio arc. Then I can show this beautiful montage, again, made from the Chandra X-ray Observatory, showing the diffuse and point-like emission in this region, kind of traced in blue and white. You can see the Hubble Space Telescope, near-infrared NICMAS data showing up in yellow, and that's really tracing the edges of molecular clouds that have been strongly ionized by massive clusters that we know are in this region. And then we also have the red color here is from the Spitzer Space Telescope in the 8 micron band. And so one of the things that's really important to know is that in addition to the Sagittarius star and the energetics that are happening on quite small scales there, the overall energetics in this region of the galaxy really seem to be dominated by activity associated with massive star formation. So this, you can see these are 3 zoomed in images of some spectacular clusters that help to illuminate the edges of the molecular material. So this is the quintuplet cluster, the Arches cluster, and then of course the central cluster, which is located down here surrounding Sagittarius star. And so there's a lot of open questions in understanding the star formation in this region. We know the region is rich in materials for star formation, but the star formation rate that we observe is a little bit below predicted rates. And there's also an episodic component that must happen. One of the things to think about is the timescales needed for clouds to overcome the extreme turbulence in this region. And so there's just a lot of exciting work happening on really trying to understand how did these clusters like the quintuplet and the Arches come to be in this environment where there's a lot of material ripe for star formation, but it may be pretty unlikely over regular timescales that clouds could collapse and form stars, and they might do it in a very unusual way. So that's important to the overall ecosystem. And what I want to turn toward now is a few thoughts about why understanding magnetic fields in this kind of environment are really critical. So of course, when you think about understanding our own galaxy, we want to turn to some nearby galaxies. And so there's been a lot of work done on magnetic fields in galactic nuclei in general. Of course, we have the best advantage in the Galactic Center because we can observe the structures at such high resolution, but you can do a lot of great stuff with nearby galaxies. And I think the advent of some higher resolution sensitive new interferometers is really going to open up this area even more. So we know that observations show that vertical magnetic fields often originate near the nucleus in some nearby galaxies, and that may help to transport energetic materials, hot plasma, out of the galaxy. So magnetic fields in terms of the nuclear region can play a role in transporting materials to very large distances and getting them sort of out of galaxies. And we'll come back to that later in the context of the Galactic Center. We also know, similar to what I just mentioned about the flows of gas, that when we study some nearby face-on galaxies where we can also compare the structure of the magnetic field as traced by polarization with the flow of gas, we can see that, that magnetic fields are often related to how gas is driven inwards through magnetic stress. And this is especially relevant in cases with barred galaxies. And so there's been some really nice work over the years done on that. So that's to set the stage for why understanding the magnetic structure in our galaxy center is really important to us understanding the flow in and the energy out of material from our galactic center. And we're in an unusual place because we kind of have to look through our galaxy in order to get a clear view of the magnetic field. So that makes it complicated, but it also makes it kind of exciting to figure out how to put together a picture. So what I'm going to do now is just take you through kind of a little bit of a montage of sort of historical, or some of these observations are older, but it gives you a sense for what we know on different size scales. So on the really big size scales, we can turn to data from WMAP or some of these microwave surveys of the sky that have been made for understanding the cosmic microwave background, but we can use these to also understand the nearby universe. So when we look on very large scales toward the center of the galaxy, we do see some organized structures that appear to be polarized and magnetic. Now, one of the challenges, of course, is we don't know the relative line of sight position of some of these things. We have to be a little careful to interpret that these things are actually at the galactic center. In fact, a number of them have been found to be much closer. But it gives us a sense that things above the center of the galaxy do have some organization and may give us some clues about potentially organized outflows from this region. There was a really striking result that came out about 10 years ago from the SPAS Australian survey. Lead author was Coretti et al. That showed that there was significant organized polarization toward the very central region. And again, this is on quite large scales. But when we zoom in to a region that's about a degree or two in latitude and maybe a degree along the plane, we can start to get more clues about what the magnetic field might be doing that's actually associated with the galactic center. We have long been aware since the mid-1990s of the lobes of emission that appear, the radio lobes, these are radio continuum lobes that again appear about a degree above and below the galactic plane. This is right centered around the radio arc, so a little offset from Sagittarius star. But you can see what's exciting about these data is they show the intrinsic magnetic field. So these data have been corrected for the effects of Faraday rotation. So this is radio continuum that has been corrected for the line of sight effects. And you can see some very well-ordered field structures that are vertical to the plane of the galaxy. So there's a component toward the center of the galaxy that is non-thermal, that is well-organized and exists on fairly large scales. So this panel on the left is a zoom in of the radio arc panel. And you can see that that well-organized vertical orientation of the fields extends roughly into that lobe above and below the center of the galaxy. If we zoom in a little further, so this is on the scale of sort of a few hundred parsecs. If we zoom in a little further, one thing that has also been discovered recently has been that there's actually very well-ordered fields in an opposite direction that are embedded in the molecular component of the center of the galaxy. So I talked about this rich molecular environment, which is ripe for forming stars, some of which has actually formed stars. And there have been some fantastic observations, balloon-borne observations, which have allowed us to understand what the magnetic field is doing within these molecular clumps that we associate with the various star formation and other features. And what we see from these data is a remarkably well-ordered magnetic field that is slightly tilted relative to the galactic plane and tends to be aligned along the molecular cloud lengths. And I also mentioned earlier that the molecular clouds in this region are quite stretched. We think possibly tidally stretched along the plane. And so the magnetic field as traced by dust in these clouds also shares that same orientation. So this is now quite a contrasting set of field systems. We've got these large ordered non-thermal fields, and they're in contrast to a well-ordered field in the thermal component. And this is borne out on smaller scales. I'm just here highlighting a couple of results that have been established over the years, showing some of our familiar molecular clouds. We're now zooming in. This is some of the sources that are more associated with the active star formation region. So these are the arch filaments complex, the sickle, and the clouds associated with the circumnuclear disk, and lower resolution observations made by the South Pole Telescope again show fantastic alignment of the dust organized magnetic field within these clouds. A lot of these results have been improved with the advent of SOFIA, and I have an image coming up next from the HAWK Plus instrument. But these data are important to set the stage again for the fact that the field in the clouds is doing significantly different, has a significantly different orientation than the fields as traced by the filaments. So we're going to zoom in further here, and these are two, again, spectacular images and results showing the neutral gas associated with the circumnuclear disk and the spiral arms that lead in and potentially feed the supermassive black hole at Sagittarius star. And you can see these are data from the JCMT, the SMA, and some modeling that show, again, alignment within the cloud structure of the magnetic field. And then this is a representation of data made with the SOFIA forecast and HAWK Plus instrument. The streamlines here show the magnetic field direction at 53 microns. These should all say microns, sorry about that, with stars provided from the 2 micron data. And so you can see very clear organization of the fields in the thermal component tracing that flow of gas. And this extends even further when you look at a region that's less than 1 parsec associated with the Sagittarius northern arm. And so again, you can see these, this representation shows the warm dusty filaments in the Galactic Center mini spiral. These are observations made at 12.5 microns. And you can see coherent magnetic field emission predominantly in the north-south in the northern arm, may be related to the orbital motions inclined to the general flow of the northern arm. So again, on the very small scales, from larger scales to smaller scales in the thermal component in the Galactic Center, the field often is aligned along the cloud structures. Now I want to turn toward a very different tracer of the magnetic field, one that connects the few hundred parsec outflow scales to these smaller scales that we also see in clouds. And so these, of course, are the non-thermal filaments that many of us have seen, and now we see them in even more stunning detail by the Meerkat radio telescope. There's been several papers that have come out even this week that just, again, show over and over again the much richer abundance of these non-thermal filaments than we have previously known. So again, just to orient you, this is the spectacular 20 centimeter image, and this is that central molecular zone shown here roughly by the arrow on the bottom of the figure. So a little history here and a little bit of observational properties of these fields. This was my attempt when I was a graduate student to make a similar image of this region. You can see the Meerkat image is much improved, but we were pretty excited about this image when it came out in the late 90s. And this image was very typical representation of what we know about these beautiful filaments that are strongly polarized and appear to trace a magnetic field component that's outside of the molecular and ionized clouds. And so just to give an overview, these are many tens of parsecs, in some cases long. They're also very, very narrow. In some high resolution studies, we've been able to resolve filaments. The filaments often break into multiple strands when you look at very high resolution. They have very strong polarization where polarization studies have been done. So we see examples of how the total intensity is mirrored almost perfectly by the polarized intensity. And so we have up to 60, 70% fractional polarizations when you look at some of the brightest filaments. We can also study the alignment of the intrinsic magnetic field by correcting for Faraday rotation. And so you see in this bottom panel, which is a beautiful filament, you can see that the magnetic field actually traces and even starts to bifurcate, and the field vectors bear that out. When you calculate the equipartition field strengths using a variety of assumptions, you tend to get field strengths of about 100 to a few hundred microgauss. And some of the most recent work that I'll show at the end of the talk has also validated that that is a typical strength in these filaments. And again, here's just a great example from many years ago, now much better done with Meerkat, of the total intensity and then the very strong polarization that you see, especially in the centers of these filaments. So here is just one page of the multiple page catalog in the new paper by Haywood et al. And you can see that not only were some of the filaments I showed that have been previously studied by the VLA evident in much greater detail. You can see the filaments are longer in extent with multiple strands, but you can actually, for the first time, and I think this is one of the most stunning aspects of their work, you can see that there are multiple field systems that have parallel strands that look a lot like the kind of classic radio arc that was identified as one of the first filament groups. And so I think that's really, really exciting to our understanding of the filaments, is that the radio arc is not as unique as we maybe previously had thought. It's still the brightest complex in the Galactic Center region, but that may be because of its association with the bright star formation happening in that region. But we can now see multiple examples. So here's the radio arc here for comparison, and we can see multiple examples of filaments that have the multiple parallel strands. So the new data by Meerkat show a much more dynamic and complex morphology than previous studies have uncovered, although there have been some fantastic VLA catalogs of filaments as well. So many of these were presumed to be there from studies of the VLA, but just the data were not as sensitive or nearly high resolution over such a wide field of view. So I thought I'd just turn to a couple of the exciting open questions, and then I'll summarize a little bit of my group's work before we wrap up here. So the things that we still are hoping to learn about the non-thermal filaments and therefore the magnetic field in the Galactic Center are the following. One is that although we have a better understanding now of the large-scale energetics of the Galactic Center, I think the origin of the relativistic particles in the non-thermal filaments is still kind of an open question. I think a really big open question are the connection of these non-thermal filaments to all of the local ISM structures. So throughout these images, you see that these magnetic strands are intimately connected with the local ISM regions. And in some cases, there are point-like sources that seem to be associated and embedded within the filaments themselves, which is something that my group is working on. We also are very curious about the polarization properties of the non-thermal filaments. I think these images are stunning from Meerkat, but they don't reveal the full extent of information that's there, the intrinsic magnetic field and the rotation measure. And ultimately, we want to know how these small localized magnetic structures correspond to some of those larger scale structures that I talked about, both associated with potential outflows from the Galactic Center, but also associated with the magnetic field structures that we know exist within the molecular clouds that these filaments appear to be engaging with. So still a lot of work to be done on these filaments. So I'm just going to take you on a little bit of a whirlwind tour of the kinds of things we've been working on in my research group related to these non-thermal filaments and how that connects to the overall questions about understanding the magnetic field in the Galactic Center. So there's 3 studies. I'm just going to show a few highlights from each one. One has been a very detailed radiopolarimetric study of the radio arc. And the reason this is important is that when the VLA was upgraded, one of the huge improvements was the capability to do spectropolarimetry over many, many gigahertz, compared to the time when we just had a couple of frequencies to do our rotation measure fitting across. So that was really a key kind of pilot experiment to see if this was going to be able to reveal some new clues to these filament structures using the VLA. We also have taken advantage of the Australia Telescope Compact Array to do a very broadband study where we looked carefully at the rotation measure synthesis data to see if that could reveal some additional clues. And then recently we've been focused on following up with detailed VLA polarimetric observations of some of the fantastic filament clusters found in the Meerkat images. So this is our version. This is a 6 centimeter image, or actually, sorry, S-band image of the radio arc. So the new Meerkat image is even more stunning, but you can start to see that this image also revealed some of the structures that were in the Meerkat image. So there's a collection of very interesting point sources and filamentary structures here that begin to come out in our data. One of the things that we were really struck by in this sort of updated and improved image of the radio arc was the potential interaction of the radio arc with this beautiful radio shell, which is associated with the star formation in the Sickle region. And so that was one of the questions that drove our work is, could some of the properties we observe in the radio arc actually be connected to potentially a crossing or an interaction with this radio shell? We also have been exploring very detailed work where we can see substructures and even potentially point sources embedded within the filament. So these are just some zoomed in images from our X and C band data at very high resolution. So here you can see you're resolving the filaments in the right-hand panel into very, very narrow strands. These are some of the brighter parts of the radio arc, and you can see that they get striated into these sort of subfilaments. So this image has a resolution of less than an arc second, which is fraction of a parsec at the Galactic Center. One of the most striking results from our radio arc study that was a little unexpected was that we saw significant polarization between the radio strands. And that really puzzled us. And had been seen in some earlier observations, but we got to see it in a lot of detail. This allowed us to do a careful rotation measure study across many, many channels, many more than we ever had access to in previous data sets, so that we could get very reliable fits for the rotation measures, which are quite high toward this region. But one of the most puzzling things we uncovered was that unlike a lot of the isolated filaments where we saw very uniform agreement with the magnetic field vectors, in this more complex region, we saw the magnetic field, intrinsic magnetic field really switch by about 90 degrees and kind of a repeating pattern across the radio arc. And so one of the things we've been exploring is, could the potential overlap or intervention of the radio shell actually be responsible for causing this change of magnetic field pattern? And so that's been one of the things we've been working on in some of our modeling. And so you can see we had some different ideas for how, if the radio shell was kind of a spherical structure with some components of it in front of the arc, some components behind, and the shell had any kind of magnetic component, we could actually be having a superposition of magnetic field components when we were observing the radio arc. And our data from the Australia Telescope Compact Array have helped us understand that a little further. This data set in a follow-up paper actually had complete coverage between 1 and 11 gigahertz, which allows you to do better rotation measure synthesis analysis. And so the question for this paper was, what was the nature of those screens? We wanted to test the idea about the radio shell being intimately involved. And we did find that it was likely that the best fits to our rotation measure synthesis showed that external Faraday rotation due to this superposition was the likely explanation of our data. And then I want to just wrap up here in the next few minutes by showing a couple of our images at higher resolution, at higher frequency, of some of the most unusual complexes of filaments in the MeerKAT data. So we chose 3 different fields, and this is work that Dylan Perret is currently working on as he finishes his PhD this spring. And we chose 3 different regions to follow up on at high frequency. So this is C and X band to complement MeerKAT's L band. And the goals here were to uncover the detailed higher resolution structure and total intensity to sort of figure out whether or not these systems were similar to the radio arc in their properties, and also to confirm their polarization, which is not yet part of the MeerKAT data that has been published. And ultimately to determine whether or not the magnetic field and rotation measure patterns really are similarly intermixed with the surrounding interstellar medium, like we did see in the radio arc. And so I'm just going to show, we're just in the process of working through the total intensity part. We don't have our polarization images yet, but I thought I'd just show a few highlights from our data. So these are images again at C band, which will nicely complement the MeerKAT images. And you can see very clearly that this is a filament group that's not the radio arc. It's one of the ones that's that we chose that's off the plane of the Galactic Center. And you can see a very similar pattern of multiple repeating filaments. We can see a very unusual point source, which appears to have some kind of emission elongated associated with it. And again, lots of point sources embedded at the tail end of this filament group. We also see, again, additional structures. These have been highlighted by MeerKAT, but again, these are 6 gigahertz images that we will have to explore that show new groups of these non-thermal filament complexes. And here's another really beautiful filament organized in a very different orientation, more along the plane of the galaxy as opposed to being roughly perpendicular to the plane of the galaxy. So we're in the process of doing the polarization and rotation measure toward these new filaments, and then doing a careful comparison with what they can tell us about the ways in which these filaments interact with the surrounding interstellar medium. I want to just end my talk by talking about the ways in which these non-thermal filaments on smaller scales have been already begun to be connected to larger scale outflows. And so I'm going to highlight in these next 2 slides 2 really fantastic results coming out of the MeerKAT images, which, you know, again, are really remarkable. So this was a result that was published in 2010 in Nature, that added another dimension to our image of the Galactic Center. So here you see a beautiful image with very high contrast showing our central molecular zone. Here's the plane of the galaxy again, Sag A star, Sag C, and also Sag B2. And here what you're seeing is a much higher and lower latitude image and in radio continuum, and you can start to see, because of the very high sensitivity, a beautiful shell-like structure emanating above and below the galactic plane. This has also been found to correspond to some recent work in the X-ray that also shows excess X-ray plasma associated essentially with at least the southern lobe. And so these bubbles are thought to energetically arise from either star formation activities or an episode associated with Sag A star, or both. And one of the really nice outcomes of this paper is it talks about how the large scale flow could actually explain the preponderance of these filamentary pieces as being part of this overall flow that are lit up by energetic particles in this region that are tracing little pieces of the magnetic field associated with this flow. And then very recently, in fact, earlier this week, there was a statistical study done of the filaments in the Galactic Center. And this is really, really exciting because this is one of the first times that we've been able to try to look at the properties of these filaments as a whole, as opposed to an individual filament group, one at a time, which is what I have spent more of my time doing. But this paper is really, really significant because they were able to take the group of filaments and look at them as a whole. And one of the techniques that they had to employ in order to do this, as you can imagine, was a technique where the large scale emission was filtered out of the image so that you could really focus on the high resolution filamentary structures. And I'll just summarize a few of these recent results. This paper is just in the process of it was on the archive earlier this week, and it will appear soon in the Astrophysical Journal. But one of the outcomes was that the overall spectral index has been determined for most of the non-thermal filaments, and generally the non-thermal filament spectral indices are steeper and have more variation than a typical supernova remnants. So that helps favor the possibility that the large-scale bipolar structure is produced by past activity, energetic activity of Sag star, rather than the star formation and supernova remnant idea that this massive star formation might drive this outflow. There was equipartition fields using a set of parameters assumed to be appropriate for the Galactic Center that show that most of the magnetic field strengths range from about 100 to 400 microgauss. And given that there is a high cosmic ray pressure in the Galactic Center, these equipartition magnetic fields then imply that the magnetic field is relatively weak in the interstellar volume. So that has some implications ultimately for how we understand the energy balance in this region. So I'll close by just saying that I think there's a variety of ways to study magnetic fields in the center of the galaxy. I've taken you on a bit of a whirlwind tour, but I wanted to kind of set the stage for how powerful radio and infrared have been to our understanding of the very complex magnetic field in this region. I also think that there is so much potential to start looking at similar scales in nearby galaxies. And I think the high angular resolution observations of nearby galaxies that are set to come with sort of our next generation of facilities where we can do wideband radio continuum, multiple spectral lines, and then the polarization over many channels and frequency ranges is really going to advance our understanding of whether or not the kinds of complexity we see in our galactic center is actually just typical for a galaxy, or is this really unique to things that are happening at our galactic center? So I'll end there, and I'm happy to take questions.
Thank you, Cornelia, very, very much for these remarkable images and up-to-date results. So really impressive. So we have already some questions, and also some people can write more in this Q&A form. So I would also.
Should I stop sharing my screen, Anna? Is that good?
Oh, no, I think it would be, please leave, because maybe the questions, there were some questions during your talk. Some of the filaments in the Meerkat images seem to be misaligned.
I'll put my favorite image back on here. Here we go. There we go.
Okay, so I think it was when you had a slide from non-thermal filaments, exciting open questions, and the question appeared. Some of the filaments in the Meerkat images seem to be misaligned. Why is that? I also forwarded you by the chat.
Yeah, so I think by misaligned, we mean that there's a sort of a traditional story that maybe historically we used to think that the filaments were all exactly vertical to the magnetic field or to the plane of the galaxy. And now the Meerkat image is showing some filaments that don't kind of ascribe to that narrative. Is that kind of the question, that misaligned must mean not totally aligned to the galactic plane? Is that, yeah, okay, great. Well, I think that is an open question. I think that is something that has been very surprising to us. I think a lot of us who worked on the brightest filaments had kind of a different story in our head of what these might be. And we looked to nearby galaxies where there were very strong chimney-like structures to sort of tell a story that it was very simple. I think now the story is more complicated, and it probably involves that outflow of very hot energetic material that is probably pulling along material as it exits the galaxy, and it's probably pulling along structures, causing different structures to be aligned and misaligned as the local energetics dominate. So that would be my understanding of that. I think that's actually something that we're working a lot on. I think actually the combination of the big picture study plus the very small individual study of filament groups is going to help us understand the answer to that question.
Okay, thank you. And could you comment on how the striking vertical B-field structures perpendicular to the galactic disk form?
Yeah, so those would be on very large scales. I think, so I think again, that it partly has to do with the activities. One of the reasons I spent some time talking at the beginning of the talk about let's see, let me see. I'm looking in the, I can see in the Q&A too, right. Okay, so the very large scale vertical structures may be related either to the energetic star formation, generations of stars being formed and exuding energy in the central region, or they may be related to the episodic activity that we know Sagittarius star underwent. And so I think in either case, you would have hot material that would need sort of buoyantly to have to rise out of the galactic center. And so that interplay between the magnetic fields helping to channel it out or being pulled along with the material is what we think, in other galaxies at least, causes those large vertical structures. And so I think we're in an unusual and kind of exciting position where we can use the detailed observations to try to help us connect, you know, how does that actually work? It's probably not nearly as clean as we think with one chimney with two walls where everything's just going up exactly straight. It's actually probably quite interesting with a lot of these twists and turns. And so I think actually our Galactic Center allows us to study that process in a detail that we, at least, you know, not right now, we can't do this in too many other galaxies that have similar properties.
Okay, thank you. And also another questions you can also read in your chat or in the Q&A. Are the point sources associated with the NTF variable sources?
That's a good question. Hi, Bob. Nice to see you online. Let's see. We don't know a lot about those point sources yet. In a couple of cases, we have studied them in detail, and we don't see evidence for a lot of variability. So at the moment, we're just interested in the highest resolution observations, which can show us, you know, do those point sources have lobe-like structure? So one of the results that came out in the recent Haywood paper right here is that there are some point-like structures associated with some of these new NTFs. And then there are also sometimes point sources in the Galactic Center that when you get to look at high sensitivity, high resolution, you can actually see lobe-like structures. This could potentially be an extragalactic source that's just in the field. But then some of the sources we're most interested in are actually the ones that seem to be embedded within the filaments. They tend to have very, very falling spectral indices. So there's a very unusual object N3 that's right in the middle of the radio arc. And we are still, the jury's really still out on what the origin of that source is. Let me see if I can find oh, it's just outside of the field here. Anyway, N3 is one of the brightest individual point sources right in here. We were unable to detect it with the VLBA. We probably need to go back and try again, but it's a very unusual bright source. We wrote a paper about that source in 2018, so.
Okay, so the next question. So given the claim that the NTFs may trace bubbles from historical Sagittarius A star activity, do we think that any of these could also be tracing current jet activity?
I'm not surprised that Sarah asked me that question, and I'm looking forward to chatting with her research group in a little while. I think we don't totally know. I think there have been some very suggestive studies right near Sagittarius star. There was a recent paper by Zhenhui Zhao and Mark Morris showing, and I don't think I have probably don't have a zoomed in region that I can show, but when you look in the region right around Sagittarius star, in this region here, which is completely saturated in this image, you do see some very unusual non-thermal filaments that seem to have similar properties to these more global ones. And so there has been some discussion about whether or not those are associated with current jet activity from Sagittarius star.
Okay, and based on the observation available, would you say that the B-field structures in the center of the Milky Way is typical of large spiral galaxies?
My sense is that our galaxy is not that unusual. I think when we start to look in detail at some of our nearest neighbors, when we go back, I have a slide showing some of the work that we've been able to do in these galaxies. I think NGC 253 is a really interesting example. It has a lot of fantastic magnetic structure toward the center, and it has a lot of really interesting radio continuum structure. And so my feeling is that probably these types of filaments are there in other galaxies. I'm not quite sure when and if we're ever going to see them, but I think understanding them in our galaxy will help us understand them in the next sort of group of the nearest normal spiral galaxies.
Okay, and the last questions, if you would like to answer, about the observation of alternating regions of aligned and orthogonal B field along some filaments. Similar behavior has sometimes been observed along the AGN jets. Could this represent changes in conditions along the filaments leading to dominance of different components of the local field in different regions, and evidence that the alternation is periodic?
That's a really interesting question. I should read more. I would love a reference there, or I should read more about that, because we were actually very surprised to find, let me get to this image of the alternate. We were very surprised to find this pattern in our data when we looked at the radio arc. We really expected that earlier observations that had hinted at this, we sort of expected that using the VLA with all of its spectropolarimetry capacity, we were going to uncover a more traditional pattern, which would show that the magnetic field was strongly aligned along the filaments. So we were surprised to find this, and I think we're still in the early days of understanding, is it really the superposition? Could it be something else, like perhaps is suggested in the question? Is there something else that we should look at? And so one of the exciting parts of our upcoming work on these new filament systems is it gives us an opportunity, because we have polarization and rotation measure data for these filaments now in hand. That's what Dylan is going to be working on this spring. It'll give us an opportunity to see, is this common to systems where you have multiple strands and a complex, rich interstellar environment, or is this more typical, or was that very unusual only associated with the radio arc?
Okay, thank you. And really the last questions, so
Okay.
Still we have 2 minutes, I hope. Have you seen evidence of an ordered large-scale toroidal magnetic field in Galactic Center observation, larger scale than filaments?
I don't think there's a lot of evidence for a toroidal magnetic field. There certainly is larger scale evidence on scales larger than the filaments for a poloidal structure, but I think, again, where we are really challenged is right at that interface between the sort of 50 parsec to 200 parsec scale. And I think some of that is a sensitivity issue, that any kind of tracer in that region might be really faint. And so it's hard for us to see it. Plus we're in the galaxy and it's harder to see that kind of those larger scale patterns. But what we haven't done a lot of in our group is, and something we should do, is connect the work that's being done using point sources through the galaxy. So there's some beautiful work being made to try to map out the magnetic field on larger scales in the galaxy. And I think we could probably benefit from trying to connect our work there. The other thing that you can do is rotation measure. There's I don't have the slide ready to go, otherwise I'd show you, but there have been some, and this is something that Dylan's working on in his final work as well, is looking at the overall rotation measure pattern. So you can say, is the sign negative or positive over the whole region of the galactic center? And that, again, that would be telling you about the line of sight field, but that might allow you to figure out whether or not we're more similar to a poloidal or toroidal, or how the field systems that we see toward the galactic center would connect to the overall galactic magnetic field. So that's something we have yet to do that I think probably should be done for those of us studying the magnetic field in the galaxy.
Okay, thank you very much. So more to do.
Yeah.
So thank you, Cornelia, very, very much. And let me invite you for the next seminar. The next seminar is...
Oh, yeah. Let me stop sharing my screen because you need to share.
So,
there you go.
Yes, Benita will share. So we have the Juan Clement on 14th March, exploring the lowest mass objects at the highest angular resolution, low mass stars, ultra cool dwarfs. So please be with us in March and be ready already for May when we invite Mar Metua. And remember about our EVN symposium and EVN user meeting in July 22 in Cork Island. Thank you very much, all of you.